So welcome. So this is the continuation, and we just finished doing these derivations, I suppose, where we got these two very important equations. And I can tell you now that one or other of, maybe both of them, but one or other for sure is going to be on your test somewhere. So it's money in the bank. Make sure you know them. Make sure you know what the letters stand for. Of course, it's classic, you know, KX. Man, didn't we have that in an equation before? Yeah, but K meant something different. You know, it's like, so watch out for all that. Here's an example. Let's do this. Can you, oh, yes, I've got some three numbers at the bottom. So can you have a go at that, please, for me? Oh, I even give you, oh man, I even give you the equation. I don't believe that.
You didn't online.
I didn't online?
No.
Oh, that's probably for me then.
I know, I didn't get that.
So when you just do it, it's a
Oh, yeah,
it's a
I like it.
gift from me to you. So let's see. Yeah, I'll do it in a minute. I'll give you 2 minutes, and we'll try and do it in 2 minutes. Oh man, I even say work in radians. Man. So, yeah, let's. I feel a bit bad cutting it so short, but I want to get a move on. So, and it is at this point plug and chug. And people are saying A, and let's just have a quick look at that. So basically, what would I do? Basically, I'd say, well, a sinusoidal wave has an amplitude, so my A is equal to 3 meters. It has a wavelength, so my lambda is equal to 2 meters. It has a velocity, so my v is equal to 4 meters per second. And I'm going to underline to the right, because that's going to tell me what sign I need. And then what is the y-axis displacement? So that's I don't know. Of a point, well, my x is equal to 5 meters, and my t is equal to 1.2 seconds. And notice, please, you know, it's kind of like, I'm not telling you that x is 5 meters. You've got to interpret from the words what the letters stand for. In fact, I could have said, I simply move this thing to the right and let it go, in which case I tell you the amplitude kind of thing. And then the rest is, all right, I recognize my equation. I gave you it in this case, but I recognize my equation. There's two to pick from, and this is classically going to be in the first one. So I say, well, y is equal to a sine 2 pi over lambda x minus vt. And then I just put my numbers in. Why do I put my numbers in? Why don't I just get my calculator out? Because if I mess up, I want, you know, that guy to know that at least I was putting things in the right place. So my lambda was 2 meters. And x was 5 minus v, and my v was 4, and my t is 1.2. Now, notice, you know, it's coming from the right, going to the right, it's positive going wave, so it's a negative sign in there, so I've got to be careful about that. And then I'd go, well, y is equal to 3 sine, and then I have 2 pi over 2, 5 minus 4.8, I think that is. 4 2s are 8, yeah, 4.8. So y is equal to 3 sine, 2 pi over 2, 5 minus point, that's going to be 0.2, isn't it? So that would be 3 sine, the 2's cancel, 0.2 pi. So I got down to there, and then I say, okay, y is equal to, and I get my handy-dandy calculator. And the nice thing about these little calculators is, written on the front of the display, it says if you're in radians or degrees. If you have the classic graphing calculator, it doesn't tell you. You've got to go to mode to check. So I can look at this and I can say, oh yeah, I'm in radians. That's good. It's a good habit, by the way, to kind of decide on your calculator what mode to leave your calculator in. And then just always go back to that. So you know I'm always in degrees. So if I want radians, I've got to change the mode. And after I've used radians, I'll change the mode back to degrees because I always leave my calculator in degrees. You know, that's when I had the graphing calculator, that's what I do. Now it just tells me on the front what I got, so I'm a bit more laxed. And then I'm going to turn around and say, oh, so I'm in degrees. I want to have sine, so I'm going to go sine parentheses, and it's going to be 0.2 times pi. This calculator has a little pi button on, which is kind of nice, and that equals, and then I'm going to multiply that by 3. So that's going to be 1.76. Is that right? 1.76 is a positive value, so plus 1.76. Yep. Meters. You put it in a box. So when I'm grading, I look to see is the answer right or not. I look to see is the equation right or not. Even if you get it right, I'll glance through the work, but I'm glancing through the work to see that it's not some weird method that amazingly gets you the right answer. Especially because sometimes the math is wrong and yet you get the right answer. Then I'm like all over it. I'll spend a fair amount of time kind of dissecting how it's impossible that can happen. If you get the wrong answer, I can easily look at this and say, well, hold on, they got the equation. What did they do? And then I can try and figure out what you did. And you get a little bit of credit or a little bit more credit. I don't go into 1,000 shades. It's like, it's usually, if you got the equation, I'll be comfortable giving you 1/4 of the points. It's like, you got the equation. Okay. If you got a little slip at the end, like you did all the work, and then at the end you said, oh yeah, it's 0.2 pi. No, that's not a good one. No, that's not a good example. Let's say here, you transcribed and you put the over 2, I'm pointing and you can't see. If you put that down one time and then down here you didn't put it down. That's more of a transcription thing. That's okay, I'm going to be concerned about that, but not as much. And there's some pitfalls, like let's say you put the positive sign rather than negative sign. Well, okay, it's kind of like I've warned you about it, so it's more serious than if I hadn't warned you about it. But again, I'll take that into account. So I don't do a million shades. I mark everybody's paper at once. All question 1, then all question 2, then all question 3. And what I do is some questions I'll be mean because I think, hey, they need to know this. And then other questions I'll be kind, but I'll be kind to everybody and mean to everybody. It's like I can't say I'm right, but I try to be fair. That's the only thing I can do. Yes.
I have a question. Like, for example, you will always have to give us the direction of the velocity, right?
Oh, yeah, but otherwise you can't. You don't know which sign to use. Yeah. I suppose I could put bam, plus 3 meters per second or minus 3 meters per second, but even then I'm giving you it. Yeah.
How do we decide which formula to use? Like either that one or the other one? How do we decide? Like
Do you have K?
Okay.
Yeah.
That's pretty much it.
Now, I could be mean and give you a little bit of both. You know, give you one letter but not the other, and then you've got to do that conversion. But that's a more sophisticated question. By and large, especially because we're rushing in the summer, it'll be one or the other. I might put a red herring in. Actually. But by and large, it should be pretty obvious which one you're going to use. Yeah. The next one, I don't have time. You guys can do that. It's fine. Okay. Let's go back because we jumped a bit, didn't we? Yes, okay. So, all right. So we have waves. Let's just look at this. So wave speed. Think of your frequency as being, we call it cadence. It's your frequency of steps. Yeah? And think of your wavelength as being how big your steps are. And your speed is basically a combination of those two. If you're very slow but long steps, you might have the same speed as being skimmering along with little steps. So it's the combination of the two. It's the product of the two. And so V equals F lambda is like a really, 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 really important equation. Now, you know, this is the linear wavelength, and it's the frequency. We already know I can dress things up in angular terms, and we'll talk about that in a bit, you know. But again, this is one of these equations which is just, you're going to use it in light, you're going to use it in a number of places, so just make sure you know that equation. Student strides down. Student strides with a step size of 2 meters. I didn't tell you that the lambda was 2 meters, but that's what the step size represents. And a step rate of 8 strides a second, so F is equal to 8 hertz. What is our velocity? V equals F lambda. V is equal to 8 times 2, which equals 16. It's going to be meters per second. So B would be the answer for that one. That's going to keep coming back up. And it's coming back up now, actually. So if V equals F lambda, and if you remember that F is equal to 1 over the period, then V equals lambda over the period. It looks completely different, but it's basically just the same thing, yeah? And if you remember that lambda equals 2 pi over k, and the F is equal to omega over 2 pi, then you get omega over k. So k, of course, in this case being our friend, the angular wave number, not the spring constant. So we have 3 equations. But they come from each other. So I know that one really well, and I can get that one really easily. And I can work out that one. It's like, you know. Oh, one last thing. In that derivation, I made a fundamental assumption that need not always be true, but it is in this case. And that is my starting shape for the wave. I chose to make it go from the origin and then up positively and then back through the origin and down. And so I define that wave as having a sine shape. If I had decided to start it at one extreme and then go down, then I would have put a cosine instead of a sine. In the oscillations experiment, in the oscillations chapter, we moved the thing to the right and let it go. So we decided we're going to do with a sine, with a cosine term for the displacement, for the position. And things fell from there. So 2 arbitrary decisions about how we start defined what our equation was. But we stick to it. Okay? So if I want to start my oscillation, if I want to start my clock when the wave is at that maximum value, I'm not going to change the equation to a cosine. I'm going to use that phase angle effect. So I'd say, oh, in that case, then the phase angle is 90 degrees, which is pi by 2. So, and this is something where, you know, people sometimes just accept the equations and don't even think about where they come from, and they'll never worry about that. They'll just say, well, it's a cosine because it's a displacement, and it's going to be a sine because it's a wave. But then there's that next level where people try and dig a bit deeper, and then they go, why is it a sine? I don't understand why it's a sine in this case and not a cosine. And you can burn, like, you know, a weekend trying to figure out why it is that way. And it is because we decided. Okay, we take care of non-ideal wave timings by a phase angle. Okay, yeah.
Is there a reason they chose sine over cosine?
I have no idea. I honestly don't know. I think that, frankly, if you look at the physics textbooks, so sometimes, you know, I want you to go deep in your understanding. But I don't want you to get tied up on things that will just kind of distract you a bit. So that's That's something to just watch out for. This next thing we're going to do is the Y motion of a transverse wave. So we have a transverse wave, and, you know, I've done one bit already. Oh, man. Sorry. For some reason, I didn't notice this last semester. It might be every time you form you go from a word to another format, you risk things being messed up. So y equals a sine kx minus omega t for a right-going wave. So I'm assuming that wave is going to the right. Okay, so I worked out what my y position was at any point. What about its velocity? Oh, that's just dy by dt. So I can say y equals dy by dt. Why curly brackets? Why not upright d's? Why is it a curly dy by dt? Partial derivative. And you may have done those, you may not, I don't know. But, you know, you just basically can get that. And if I want the acceleration at that point, just differentiate again. So you can either learn these equations or you can derive those equations. But, you know, they're there. Next. What is the speed of a wave on a string? So this comes up in lab. We say consider a transverse wave pulse. So that's a going down a string. Taut meaning stretched. Intuitively, we would expect the wave speed to increase with string tension because it's more connected. It's like, and decrease with spring mass per unit length, really, because it's more sluggish. This is expected from Newton's laws. In fact, V equals not T over, that is the mass per unit length. It's not linearly related, it's square rooted related. And so we have this thing, and that's kind of brought out of a hat. You'll do it in lab. I'd like you to know it, but you do it in lab. Problem? No, okay, cool. Okay. Next. So this is another thing we're laying the foundations for something which will come up again a couple of times. And that is, most waves don't go on forever. They hit some kind of boundary condition, some edge, and the energy bounces back, perhaps. So you can imagine being at the swimming pool and making a crest of a wave, and it goes towards the wall, and it comes back. And if you looked carefully, you would see that crest come back as a crest. It goes up the side and comes back as a crest. But when I first came to the United States, the big fashion was everybody had water beds because they were like cool in the summer and nice and warm in the winter. And so I got a water bed. And the first thing I found out was tucking the sheets in is a real pain. Because you can't put your hand underneath it and pick up the side of your bed and shove because it's a water bed. It's like a balloon. You pick up this little bit and the little bit shape of your hand comes off. And the rest of it's still on the mattress. So it's a real pain. And putting fitted sheets in, you know, you got to... So I ended up with this technique where the corners were the hard thing. So I'd actually put the fitted sheet on the bed, on the mattress, and I would climb on top. And then I would jump, and when the wave went out and lifted the corner of the bed up because I'm pushing down, I'd shove the sheet under the corner, and then it would be trapped. So I had this like really cool technique of putting the corners in. So one day, I don't know why I was, but I jumped, and I think my phone rang or something, but I looked, and the weirdest thing happened because I jumped and I saw the crest go towards the corner and a trough came back. It was not a crest. It's not like at the swimming pool because the water bed has a tension. The end is kind of like fixed. That corner's kind of fixed. Whereas at a swimming pool, the corner's not fixed. The water can go up and down. With this, the end is kind of fixed. And what you see is that there are two modes of reflection. I can have a situation where a crest going towards the reflection comes back as a trough, and a crest going to the wall comes back as a crest. They are different. And somehow, mathematically, I have to take that into account. Because as the energy bounces back as a trough, it's going to cancel the next wave out differently than if the energy comes back as a crest. This is, unless you had a waterbed and played with it a lot, this is completely outside your sphere of activity. So you can do this by getting a piece of string and a pole and a loop and letting this thing slide up and down, and getting a piece of string and a pole and tying a knot and play with it. There's something else I'd like to show you. So let's get out of here. Are you going to let me get out of here? So I'm going to say discard. And I'm going to come out of here. And I should have done this before. I'm sorry. I'll do it now. You'll see the whole thing. So I'm going to go onto that. And I'm going to go to PHET. And you go there. And it's the University of Colorado. And you have physics simulations. You also, by the way, have chemistry for when you're doing chemistry, and circuit construction, and energy skate park, and all this kind of stuff. And it's free. And if you look at the physics, we can have sound and waves. So we're in sound and waves. And if I look here, the classic one is this. So I'm going to click on that, and I want to make it, I don't want to download it. I'm just going to make it bigger. And so we have one of these. Now, the first time I played with these things, I thought, what a total waste of time it was, because there are all these buttons. But what I realized was you've got to be logical. You've got to be sequential about it. And you've got to change one thing at a time rather than changing 5 things like I was doing and going. So you've got to learn how to use it. So this is a piece of, this is a row of oscillators forming a wave because they're connected. And I can either manually do stuff, or I can pulse it. Oops. I can pulse it. Oh, it'd be nice if I gave it some juice. Boom. I can pulse it, or I can oscillate it backwards and forwards. So 3 modes, and I want to pulse it. And then I can play down here with the amplitude. Let's make a nice big amplitude because I want to see what's going on. So I'm going to make that bigger. Let's just grab it and move. And then pulse width, I want it to be quite narrow. So let's make that smaller so it looks really sharp. And then I do want damping this first time round. So I'm going to put lots of damping. And I don't want it to go that fast, so I'm going to get rid of some tension. So clearly I know something about how it works. Hope it works. And then do that. Oh, yeah, sorry. Let's do not as much damping. Let's do no damping. And don't look at it. Well, you've got to look at it for a bit, but. Ooh! Now I've got to stop it. Oh, now I've got 2 of them. Restart. So it went as a crest and came back as a trough. Because it's got a fixed end. Let's loose end piece of string.
Okay, can you put it in slow motion?
Is there a slow motion on it?
Yeah, it's right to the right of where you are.
Okay. Oh, it's slow motion, yeah. This could take forever, you realize. Yeah.
Oh.
But we can talk about it. So you get it going, the crest is going, and now, woo, it comes back as a crest. So there's a phase difference between bouncing back from a fixed end and bouncing back from a fixed end and bouncing from a loose end. And we have to take that into account. And we think about it as, well, you jumped ahead when it comes back as a trough, when you sent a crest, at the wall, it jumped ahead by half a wavelength. Well, that's a pi phase angle, so you can take it into account. Okay. Anybody interested in teaching? Oh, come on.
Maybe later.
You know, I have a Maserati at home. I just don't show you it. It's a great life. If you're a generalist, if you're the kind of person who always wants to learn, teach, because you'll learn forever. It's a great life. But on my teacher training, I had one of these things. This was in the days of projectors, and you had this little videotape. And I learned a really important lesson because I showed what I wanted to show, and it was quite clear. And then, this is why I was a bit hesitant when you said do it in slow motion. And then some of the students said, you have to rewind it at the end. And some of the students said, reverse it. So I said, oh, why not? They want me to reverse it. I want to be popular, so I just reversed it. And all the chemical reactions started going the other way. And the class got excited. And then this student said, well, now I'm totally confused. And I realized that I had just done the worst thing. Because in playing with it, not showing what I wanted to show and stopping, I'd gone and messed things up. So that's why I was a bit, when they said do it in slow motion, it was like, do I really want to do it in slow motion? But it's important with this, don't play with it. Explore it. Change one thing at a time. It's incredibly useful. It will clear things up. And this is going to come up again with cables, like cables for your cable TV. It's going to come up again with light. And we're going to use this over and over again. So watch out for that. There is a lot of really good stuff on that thing. So let's go back to here. And so let's go back to slideshow from current slide. So watch out for that. If you get something reflecting not from a fixed end or a loose end, but just from a medium which is more dense or less dense, you get the same kind of issues. So if you get two pieces of cable and the cable connectors have not got the same resistivity as the actual wire, you'll get reflection from those junctions. And that's a real problem with connections. So, in fact, I just had my FiOS upgraded at home, 150 gigabytes or something. I don't know what it is. Megabytes. It was like, yay! And the guy was showing me. I told him I was a teacher. He was showing me how they spliced together the optical fibers. It's really quite interesting. It's where the magic comes into science and technology. Let me stop here. Art involved in the science. So next, these next bits, I got to be honest, I don't really care that much about. It's like I got to draw the line somewhere. When we used to have the equation sheets, this was all fair game. But now I'm not so worried about it. This is the total potential energy in one wavelength of a piece of string. So imagine a piece of string. Whoops. Imagine a piece of string. Imagine a piece of string. Imagine a piece of string. And imagine I got a piece of string. And, you know, it goes on like that. Well, energy's been transported. So between there and there, there's a certain amount of energy. And it manifests itself as some spring potential and some kinetic. I mean, there's bits going on. So what they do here is they start off, in this case, with the spring potential, and they work their way through. And they ask themselves, how much energy is there in that amount of material? And they come out with an answer. And the answer's down here. So, man, I'm never going to ask you to derive that. And in fact, since we got rid of the equation sheet, I'm not going to ask you to remember that. Here's the thing. I'm not that good. Here's the thing. I might give you that equation, and I might ask you to do something with it. And so you can't blow it off, and you got to know that that is the energy in one wavelength, and that is the mass per unit length, and this is the angular frequency, and that's the amplitude, and that's the wavelength. So you've got to be able to use the equation. Because what I might do is I might say, oh, plot me a graph of how the energy per wavelength is related to the amplitude. And what would it, looking at that graph, what would it look like? Yeah, it would be, because that's squared and that's not. And all these things are constant. They're all 1, yeah? That's a fair game thing. Testing D, it's an easy question when you think about it, but you've got to know what the things stand for. Okay? Now, from a physics point of view, isn't it kind of curious that the energy in a wavelength, if I double the amplitude, I get 4 times the energy? You might not guess that. It's kind of interesting. Double the amplitude, I get 4 times the energy. Clearly, the longer the wavelength, the more energy is in it. And clearly, the bigger the mass per unit length, the more energy that's in it. And clearly, the higher the frequency, the more energy is in it, but it goes with frequency squared. Yes?
What mu stand out for again?
Sorry?
Mu?
Mass per unit length. Okay.
So is all of that just like a derivation?
That's all a derivation, yeah. And from a, you will derive things in your careers. So it's nice to see derivations every now and then. But honestly, it's kind of the difference between your generation and my generation is in my generation, we'd learn some of those derivations, and that's what we'd be tested on. And, did you know what it meant? I'm not sure they tested on that so much. It's just, could you finagle the answer? And in a way, I think physics has changed for a good thing, that we don't do as much as that. There are times when we do derivations, as you did in Physics 1, if you're with me, but more specifically. If we do the kinetic energy, we get the same answer. And if we got the total mechanical energy, we just add the 2 answers together. So that's a bit of conceptual stuff. Yeah? If I take the kinetic energy in one wavelength and it's 20 joules, and I tell you that then I've told you that the potential energy in that wavelength must be 20 joules, because remember the pendulum? You had as much kinetic, the maximum of your kinetic was equal to the maximum of your potential, because it's energy conservation. And therefore I told you the mechanical energy was 40 joules. So a nice little conceptual bit dressed up as wave stuff. The power is energy per unit time. So, and this is the case where, I think the book does stuff because it can, and it makes a section out of something that there's no need to make a section out. If you know that power equals energy per unit time, then you know to take the total amount of mechanical energy and divide it by the period. And, oh yeah, lambda over t is velocity. So I end up with this new equation, but it's like, in a way, it's not a new equation. It's just one slight variation on the old equation. So again, know what that stands for, but you don't need to know that equation. Okay? Yeah.
What's the unit of power?
Watt. Yeah. Watt. Joule per second is also acceptable. It's the watt. And that's why I got rid of the equation sheets, because people using the equation sheet would give me a pressure equation for a power. It was like, they're not even in the same chapter. What's going on? Well, it's P, isn't it? So, this last bit, if you continue with mechanical engineering or you continue with physics, you're going to do this a lot. But this is basically the linear wave equation. And you've seen it. And you don't need to know it. You've seen it. That's fine. Okay, cool. Let me stop there.